So I'm Dhruva. I'm going to talk about breaking models, how, why, and when. I guess I'm not really that sure about your background, so I'll try and do something. I'm trying to do something a little bit open-ended, and we'll see how it goes. So today's goals. So as data scientists, I guess most of you have experience in what I'd call data-driven modeling. My experience, my background is a little bit more in what I'd call mechanistic modeling. And I think it's just useful as a general thing to actually look at the shared insights and the differences between those two paradigms and what one can learn from the other. So I'm going to introduce a little bit of the shared commonalities and differences. No? Okay. Then I'm going to talk about some of the issues I had that I tried to deal with in a past life about interpreting mechanistic models, which I think have some consequences in interpretability of data-driven models, which is an important topic in various domains. And then I'm going to suggest some future research efforts, which I'm keen to find people interested in joining in kind of adapting what I was doing for mechanistic modeling to some data science problems that I think are of interest. Oh, now I'm speaking loudly. Wow. So a little bit about me. I'm actually a neuroscientist. So my principal relationship with modeling is to get scientific insight. I'm interested in how neural circuits function. In particular, I'm interested in Drosophila, the fruit fly right now. So I'm not going to go into that, don't worry. I'm not the kind of scientist who runs a wet lab, though, where I actually deal with neural tissue. I'm a computational neuroscientist. So mainly, I try and understand the functional principles of the brain just using a computer and paper. And that reflects my slightly meandering path to get there, because previously I did my PhD in the general paradigm of trying to figure out how to use powerful computational models to get scientific insight, in particular their use and abuse. So the whole Superman trope, with great power comes great responsibility. We're getting increasingly complicated computational models permeating a lot of scientific spaces, and sometimes they can give great conclusions, and sometimes you can get very confident nonsense. So gonna think a little bit about that. And that's what I'm going to talk about mainly today. So I'm going to talk about some of the issues in interpretability in computational models. And from there, as I said, I'm going to go into some future directions, which, as I said, I'd be really interested to explore with collaborators or anyone interested, which relate to making and breaking hypotheses which we get from statistical models. I like XKCD cartoons, so they do much better slides than me. So I just thought I'd give you a moment to do this. It's tongue-in-cheek, don't worry. Now, what's the point of this? Any computational model, what we're fundamentally doing is we're getting a load of data. We're somehow incorporating it in a particular kind of model. And once we've synchronized the model and the data through training or whatever you call it, we try and get some insights. So yeah, the first part of actually getting the model to incorporate the data is often called training. And the second part you might call prediction or interpretation. And what that XKCD cartoon was referring to is the temptation to actually go backwards and try and train your model and structure your model to get the insights you want to. And I guess a high-level goal of what I'm going to talk about is a way of making sure that's not implicitly happening. So let's think a little bit more concretely about what happens when we train a model. Let's say we have some neural network, or it could be a random forest, any kind of model. So any model has parameters. These are the tweakable quantities, the things you change to change the behavior of the model, change how it interprets and processes inputs. And when you feed it with data, some training algorithm, backpropagation or whatever, tweaks the parameters based on the data. That's the process of training. Until eventually, you have a model which gives predictions from inputs that reflect real life in some way. So as a toy example, I could train a neural network on a load of data about clinical data about people's lifestyle factors, like their health and their genetic fingerprints. And I could train it to give predictions on the probability of getting a particular type of cancer. That's a very standard data science exercise, right? This is a small subset of the metabolic reaction pathways that are downstream of a kind of genetic mutation that gives you cancer. So, I'm not going to interpret it, don't worry. I don't even have a clue about it. But proteins get upregulated, dysregulated. Cancer is a really complicated process. And when we do data science, usually the structure of our model and the structure of our system are entirely different. That's not necessarily a problem, but it's something we should note. So a neural network, it has a very particular structure with weights and nodes, and nodes. Doesn't look anything like the model system, but somehow through training, we get them to have similar input-output relationships. By the way, before I should interject, please feel free to interject at any point. There's nothing worse than just blankly listening to something when you lost something 5 minutes ago. Like, I'm happy to take questions or online. Now I'm going to introduce two extremal ends of modeling, I guess, which most modeling often falls in between. So the first extreme is data-driven modeling, i.e. data science, where, as I said, your model structure looks nothing like your system structure, but that's okay, because the kind of model structure that's good in data science is one that can fit anything. You want like the best, biggest neural network that can just do anything. And the point of that is pure prediction. You've got loads of inputs, you might have loads of labels if you're doing supervised learning, and you want to fit the inputs to the labels with your model. The issues with this are, if your system structure looks nothing like your model structure, it's very, very data hungry. And it's only relevant for a single data distribution. What do I mean by that? Let's say I did a clinical trial getting loads of cancer outcomes in a group of people, and they all had a particular ethnicity and gender. There might be a very different group of the relationship between risk factors and outcomes might be very different for a different ethnicity and gender. And a neural network that's purely data-driven wouldn't really take account of that. Now, ethnicity and gender are very obvious, observable factors that you might want to incorporate, but there's all sorts of higher-level hidden factors that could also be important that a neural network or a general data-driven approach might not deal with. So advantages and disadvantages. Here's another XKCD cartoon. So what's going on here? All of these are different methods of statistical fitting. That is, we have all these scatter plots which reflect data in some way. We don't know anything about the underlying mechanism of that's generating the data. A statistical model, whether it's linear, quadratic, logarithmic, whatever, has no actual structural similarity with whatever's generating the data. Now, these fitting methods are very good at interpolating data, but they're very bad at extrapolating data for that reason, as illustrated in the cartoon. Which leads me to another flavor of model, which has its own advantages and disadvantages. You could call this data-constrained modeling rather than data-driven modeling. Other people might call it mechanistic modeling. This is when you try and build a model structure which actually tries to reflect the structure of the system you're trying to model in some realistic way. So if my system was, the downstream metabolic pathways that cause cancer from genetic mutations, I'd actually try and model those components. And I put the dotted line because you never do it perfectly. So what's the point of this kind of model? I'm going to give a slightly more concrete example than cancer. So car models, BMW, Jaguar, whoever, they spend billions and gazillions of man-years and money on making extremely complicated mechanistic models of their cars. This is, a little Simulink a cartoon of what a vehicle suspension model might look like. And you can see it's mechanistic. They're actually trying to fit all the various different physical quantities and incorporate them explicitly in the model, rather than as a neural network. So what you need data for then, if you had the perfect mechanistic model, you wouldn't need any data. It's just, you could run Newton's laws and do your mechanical equations from first principles and you have a car. That's not realistic. Things like, for instance, the friction of tires in different conditions are very hard to get from first principles. You need data to calibrate on quantities that are hard to actually derive. And of course, it requires massive effort and complexity compared to something like a neural network. And the goals are different. The goal of this model is not just to predict what a car is going to do. The goal of a model like this is things like design, control, and robustness. So suppose I was interested in stiffening the suspension and seeing what would happen. I can use this model and I can actually explore that. If I want to build a control system for ABS braking or something, that system would actually need a good internal model of the vehicle so it knows when to brake and control the thing. And robustness. For instance, if I'm flying in an aeroplane and it has a system dealing with disturbances like wind, I better be damn sure that my control system can deal with all disturbances in a wide range that's not trained on interpolated data. It can extrapolate to scenarios that we are within feasible bounds, but we've never seen before. So these kinds of models are great for that kind of thing. And the predictions are not, the point of these models are not predictions, just checking the predictions match real life is just a form of validation. So that's a mechanistic model as opposed to a data-driven model. And the key point here is you're predicting more than you're measuring. So usually in data science, when we're fitting data, let's say supervised learning, we're learning to predict things that we're giving data on. We're just learning to predict it in new scenarios. Here, the set of things you're trying to predict is more than the set of things you're measuring. You might want to, so lots of components actually wear out and change over the lifetime of a car. You can't directly measure them, but using a model like this, you can infer from the overall dynamics of the car that, hey, the suspension's a bit soft or whatever. And that's by exploiting the structural similarity of the system and the model. So these are the kinds of models I'm more used to in science because they're more interpretable and you can use them to actually build conclusions and think about how perturbations would affect a biological system. But they have issues. And I'm going to illustrate this on the most simple mechanistic model, which is that of a pendulum that goes up and down. If any of you did like M1 in A-level or something, this is like the first kind of mechanical model you get. So you have a mass on a spring. It seems like a very weird, abstract, and strange model to choose, but it's very easy. And actually, for instance, in vehicle modeling, a lot of stuff boils down to masses and springs. Anyway, suppose you can observe this thing going up and down. So you get data on the position and the velocity. So you can see on the right-hand side, it's a damped oscillator. With a mechanistic model, as I said, you can predict more than you're measuring. So from the mechanistic model, you might actually want to predict, to infer the mass of how much the mass weighs and how stiff the spring is. Those are parameters that you could potentially measure with a mechanistic model. If anyone's interested, here's the actual equation, but doesn't matter if you're not. So what would I do if I wanted to do that kind of inference? The first thing I'd do is to train the model on the data, right? So I'd keep tweaking the parameters of my model until the model's output looked just like my observed data. And if I got the right parameter values, so I put in these values just for a joke, well, not for a joke, just for arbitrarily when I did the simulation. If I put these parameters in, I'd get a perfect fit. Great, the model has the right parameters. But you know what? If I put these parameters in, I'd also get the perfect fit. If you're interested in the equation, you can see that it's not the actual values of the mass and the spring stiffness, it's their ratios with each other that count. I could even get these values and get a perfect fit. So here I'm estimating the mass of the spring as 200 kilograms when the true thing is 2 kilograms. So I'd get completely garbage output from a perfect fit. This is called a model unidentifiability. So basically it's a situation where even if you have perfect data, and you have almost zero, absolutely zero, almost zero training and/or test error, you can still get completely garbage predictions. And that's a consequence of the fact that in these kinds of models, the set of things you're trying to predict is more than the set of things you're trying to measure. Now, that was easy to figure out the unidentifiabilities in that system because you can look at the equation. What would be the unidentifiabilities in this kind of system? It's pretty hard to actually figure out. It's an issue in mechanistic modeling. So I built an algorithm and a software package to do exactly that. So I guess the workflow is you start by training your model and then generating some hypothesis or scientific insight based on your model, whatever it is. So for instance, let's make a stupid hypothesis. Let's say we trained our model on the mass spring data and we got the hypothesis that the data indicates that the stiffness of the spring is less than 10 newtons per meter using our model. Once you've trained it using whatever algorithm or way you like, you note the parameter values relevant to your model-based hypothesis. So for instance, that would be the spring stiffness in this case. And then you generate what I call minimally disruptive curves. Basically, suppose you have the same trained model and the same data. It's a way of doing a scalable and directed search for parameters that would break the hypothesis you've built. So it's a way of trying to break the model while keeping the same model structure and the same training data. For instance, in the case of this simple mass spring system, these are the three parameters plotted, and any point on those lines, if I take a cross-section of the y-axis, that's a set of three parameters which give identical behavior. So, and that's the minimally disruptive curve. So it's a whole trajectory of parameters, a whole line of parameters that simultaneously fit the data perfectly, but break the hypothesis potentially. So why not just actually go to take your model and just like look at all the parameter values and see if all the parameter values work or don't work or break your hypothesis? This would be what I'd call a brute force method, or more implicitly a Bayesian method. Suppose I had a model with two parameters and I wanted to test my parameters at 10 values. That's 10 to the power of 2 different points I have to test, so 100 different places I have to test. Oh. Now suppose I have 10 parameters trained at 10 values. I now have 10 to the power of 10 simulations I have to do, that many tests. That's a lot of tests. That needs a lot of computing power. And if I want to do more than 10 data points or more than 10 parameters, this is called the curse of dimensionality. And it's a general problem in applied mathematics when you're trying to analyze complicated things. On the other hand, minimally disruptive curves, the trick of this is it does a directed search. It doesn't just go randomly. It's got a way of being able to kind of literally find a priori the right directions to tweak the parameters in a way to break the model hypotheses in the worst way possible. And that means that the computational burden of the algorithm scales with the complexity of your model, not the number of parameters. So it's actually applicable to quite high-dimensional big models. As I said, I'm a neuroscientist, so I'm not going to explain this graph too much, except to say this is a detailed model of a particular neuron in the lobster. We love lobster neurons because they're good at being deoxygenated and they can deal with huge temperature and pH variations. And below is a minimally disruptive curve. Basically what it's doing is it's taking a trained model and I'm asking it, hey, look, this is a kind of neuron that spikes with a particular phenotype. It has this kind of bursty phenotype. So a neuron, if you don't know, it has electrical activity, it spikes or it bursts. And what the algorithm is doing is it's finding ways to change the parameters of the model that preserve the bursting phenotype and preserve the red line, which is calcium concentration. Don't worry about what I actually mean. It's just preserve all the desired model features I want, while changing the parameters in the worst way possible to disrupt the conclusions. In this case, I was interested in the density of what are called calcium ion channels, and has found a way of disrupting them a lot while keeping the model the same. So it's a bit of an irrelevant application for this audience, but hey, I am a neuroscientist, and this is the animation I had to hand. So now I want to get from here to the unexplored, the stuff I haven't done relating to data science that I think could be an interesting application of this, and for which I'd be really interested in exploring with people here. Suppose I had a model based on clinical data where I was trying to correlate mortality to night shifts and/or smoking. Now, let's say that smoking and night shifts are correlated. People who run night shifts are more likely to smoke. It's a stressful thing. Mathematically, it's impossible to find the true correlations between either of these independent variables, night shifts and smoking, and mortality, because they're correlated. So you can get erroneous conclusions. To put it another way, I could get the same data and say, hey, look, I think night shifts are really, really highly correlated with mortality and smoking is not at all. Or I could do it the other way around. I could say smoking is really, really related with mortality and night shifts are not much. And both of those conclusions would fit the data if those two things are correlated. Hopefully you can see that, it makes sense. This is well known in stats. I'm not discovering the wheel here. And it's called multicollinearity. So when two variables are correlated, that's basically trying to say that there's a linear relationship between the variables. Here's another way of thinking about multicollinearity. We have our data, our clinical data on mortality based on those features. We fitted it But there's no one single unique set of fitted parameters, i.e. correlation coefficients, that perfectly fits the data. There's an entire space of correlation coefficients, ranging from night shifts being really high and smoking being really low, to smoking being really low, night shifts being really high. And they would generate different scientific hypotheses, wouldn't they? They'd have different clinical conclusions from that. Hi. Oh, sorry, I should use the mic more. Sorry, I hope people can hear me. Okay, great. So that's a linear space of parameters. And there's standard diagnosis tools in statistics to deal with this. I wouldn't say they're perfect, but they're there. Now here's a flashback to what we were talking about before, the mass spring system. Can you see a relationship? There's a whole linear space of parameters consistent with one particular behavior. Now I'm going to invent a new word, which is multi-co nonlinearity, which doesn't exist in the literature. What if instead of having a linear space of parameters commensurate with one particular model conclusion, there's a nonlinear space of parameters? Well, then it's not actually obvious. There are not standard tools for diagnosing. And this is where I think minimally disruptive curves could come in useful. Because it's not restricted to linear spaces of parameters. It weaves around the set of parameters in the model, trying to find ways to break your hypothesis. So, for example, I think I'd be interested in trying to achieve a goal in medical statistics. So what would that be? That would be taking an existing study on, something, risk factors for vitamin D deficiency or whatever, take the model from the paper, take the data from the paper, and then what? Use minimally disruptive curves to generate a new instantiation of the model, with the same model structure, and the same or almost as good a quality of fit, but the opposite conclusion. So for instance, suppose I read a paper with a model saying that vitamin D decreases your mortality rate. Often those models are actually not very robust. They do very incomplete and bad sensitivity analyses, and that's part of the reason why clinical studies change each year in their conclusions. What I'd be trying to do is to use minimally disruptive curves to take the same model and the same data and try to find a way of tweaking the model until it can show the opposite conclusion to what I'm interested, that vitamin D increases the mortality rate. What would be the domain of validity for this kind of thing? Well, nonlinear models, because linear models are kind of already covered with the existing literature. Those where there's a quantitative relationship between the fitted parameters and the scientific conclusion. So for instance, usually when you have one of these things like vitamin D increases your mortality rate, there is a literal correlation coefficient in that model, which when it's positive or when it's high, indicates the degree of correlation you're using scientifically. And examples, if you're interested, but don't worry if you're not, are generalized linear models or proportional hazards models, and I'm sure there's more. But those are some candidates I identified. So yeah, that would be really interesting to do. This is a bit of a side hustle for me because, as I said, I'm a neuroscientist right now. But I'd be really interested in talking to people who are interested in helping or adding insights or feedback. So yeah, that's it really. So thanks a lot for listening to me. I'd like to thank Antonis and James, who were my supervisors when I was doing my PhD and when I developed the algorithm. And Tim O'Leary, who was my supervisor when I was doing a postdoc, and was very generous to allow me in the middle of the pandemic to do this for a bit instead of doing science, because I just wasn't in the space to do science. Sometimes you just need to code, right? If you're a little bit lonely. And that's true, no? Yeah, and I'd like to thank the funding bodies. There's an old mathematical, not very readable paper about the algorithm. When I made the paper, it wasn't a really very reasonable algorithm to do, but recent advances in what's called differentiable programming, thanks to machine learning advances, have made it actually quite easy to implement these kinds of things. So I made a software package, and the QR code and the website are there, which implements this, unfortunately in Julia. Yeah. But so if you check out their website, you'll probably get the best view of what it's doing. So thanks very much for listening. That's it.